Good afternoon, everybody. Thanks for coming on a very, very, very busy week. We appreciate everybody being here. It's our delight to host this last in our guest lecture series and one of the real highlights of the year. Just a couple of quick announcements for students. This lecture is part of Ball State's Chirps Week, which is our celebration of, this is the acronym, creative works, high impact practices, research projects, and scholarships. So students who are collecting any of the Chirps credits should scan their IDs in the hallway outside if you haven't already done that. And then for faculty, we have LACES and AIA continuing ed credits. And again, sign-up sheets are outside the door. And any kind of feedback you have is always welcome. So this is a special night, and many of you have been here for the last few years, but we are honoring Ethan Whitehead, one of our own, who was studying architecture, and when he passed away in 2021, and in his honor, his parents, Julie and Doug Whitehead, established the Ethan Whitehead Guest Lecture in Sustainability. And this was really developed as a series to inform and inspire as many people as possible on a topic that was really at the other top of Ethan's interests and passions, and he was very passionate about this. And so the intention is to give every student and faculty member access to expertise through these great lectures that will perpetuate Ethan's memory and his passion for sustainability. And tonight we have a special presentation, and President Mearns has joined us to make that presentation. So President Mearns.
Thank you, Dean, and it is my honor to confer upon you this certificate of recognition in honor and in memory of Ethan. As I shared with you outside, it is remarkably inspiring how you have transformed this loss, this terrible loss, into something that benefits our faculty and our staff and our students. And you are an inspiration to all of us in terms of how you serve people and help make this world a better place for all of us to live in and for our children and grandchildren. So this is a certificate of recognition in Ethan's honor and in his memory, and please accept it on behalf of every member of the Ball State community with our great sincere appreciation. So thank you very much.
Thank you, President Mearns. So we are delighted to have our speaker here today. He's in a pioneering role, and he'll be presenting some really forward-thinking systems approaches. And to present our introduction will be Tom Collins. There he is, Professor of Architecture.
So I am thrilled to introduce Felix Heisel. He's an assistant professor and director of the Circular Construction Lab at Cornell University's College of Architecture, Art, and Planning, and a faculty fellow at the Cornell Atkinson Center for Sustainability. He's a licensed architect in Germany and a partner at 2HS Architekten und Ingenieur. I hope I got that right. An office specializing in the development of circular prototypologies. Heisel's scholarship focuses on systemic redesign of the built environment as a material depot of endless use and reconfiguration. He's published several books and articles on the topic, including Building Better, Less Different, Circular Construction and Circular Economy in 2022, Cultivated Building Materials in 2017, and Building from Waste in 2014. Heisel graduated from the Berlin University of the Arts and has been teaching and researching at universities around the world, including the Berlage Institute in the Netherlands, the Ethiopian Institute of Architecture, Building, Construction, and City Developments, the Future Cities Laboratory in Singapore, at ETH in Zurich, and at the Harvard Graduate School of Design. So join me in welcoming Felix Heisel.
Hello. Thank you very much. I hope the mic is working. Yeah. Thank you, Tom, for the introduction. Thank you to the president and the dean and everyone else who's labored behind the scenes to make this evening possible. And I hope in some small capacity this lecture will help continue the legacy of Ethan here at this school. My lecture today is titled Deconstruction and Cultivation, Advances in Circular Construction. And maybe as a kind of advance notice, of course, I have the pleasure to talk about all of this work today. I'm representing a large team that is laboring behind the scenes to make these works possible, both in my office and at Cornell University. The Circular Construction Lab is an interdisciplinary unit at Cornell University, and our mission statement is essentially to implement circular economy paradigms into an industrialized industrialized construction industry. We draw from students all across the campus. This semester we're very architecture heavy in sort of the disciplines. Last semester we had 4 mycologists and biologists in the team, civil engineers, computer scientists. So we're trying to merge disciplines to answer questions that are systemic and as thus not possible to be answered by one discipline alone. And some of the key problems that we're interested in or that we're sort of tackling as an industry are the fact that if you look at buildings over their whole life cycle, then our industry contributes to more than 50% of the resources that we take out of the Earth's crust, about 40% of carbon dioxide emissions, and more than 40% of solid waste. And so that is the imprint, right, of what we're doing here. And I think it's really important to think about how we can tackle these questions. And if you zoom a little bit more into some of these, this is the chart of global carbon emissions over the last couple hundred years. And you notice this sort of exponential growth that started with the industrialization and then continued development. But the reason why I'm showing is because essentially to stay within, so for example, the Paris goal agreements, we would need to mirror this, this chart and drastically reduce emissions very, very quickly to reduce global warming. Essentially, these are estimates by Architecture 2030, and we're sort of talking by 2030 we need a 65% reduction in emissions, which we all know our industry, 5 years is, that's basically tomorrow. That's the design phase and construction phase of one building. And so we need to act really, really quickly. And so what the lab is essentially trying to do is close that loop. And by closing that loop, we reduce the emissions that come from raw material sourcing, and not just the emissions, but also the social impacts, the environmental impacts, the labor impacts that are associated with global material sourcing. And at the same time, on this end, we're reducing the amount of waste that's going to landfill by closing that loop. And the important thing is that there are several different strategies within a circular economy that we can look at. There's, of course, recycling that we've all talked about for years. And then there's remanufacturing and reuse and several others. By now, I think we are at 7 Rs in some of the publications. But what I'm trying to show here is that the most impactful of these cycles is the smallest and the most local, and that is direct reuse. And just so that we all have the same definition at mind, if you try to define a circular economy, then it is by design a system that eliminates waste and pollution, circulates products and materials, and regenerates nature. And I'll try and cover all 3 of these main points tonight. So this all sounds fantastic. The problem is the reality looks more like this. So if we look at the end of life of a building, we are demolishing. This is an example from Ithaca, New York, where the construction manager was actually incredibly proud of what they've done. Right? They pulled out all the steel, they ground down all the concrete, they reduced landfill. But then when you start digging into these material streams, the steel was exported to China for recycling. So just the distance and the emissions associated with that distance of the travel probably offset any of the good parts that the recycling will do. And on the other side, the concrete aggregate was used as clean fill on the local landfill. So this is just renaming what is actually happening, right? We need to weigh down our landfills, and instead of using virgin rocks, we use concrete, but essentially we're putting the concrete on the landfill and calling it circular economy. And that explains a little bit what are the struggles that we're facing in this industry, right? So if you go through the material cycles quickly, we can of course recycle mineral demolition waste. We use it for roads, for aggregates. The problem with that is that the cement is actually the real problem and the aggregate isn't. And so we're not really tackling any of the environmental impacts of concrete, but we're of course at least reducing the waste. But then there are other families like glass that are technically 100% recyclable, and we're just doing a really bad job in getting the material out of the built environment in a way that is reusable or recyclable. Just for information, if you wanted to use recycled glass cullet to produce float glass, the technical limit is 1 gram of dust in a ton of material. That's the level of cleanness that you need to make float glass, right? If you look at our demolition sites, there's a little bit more than 1 gram of dust involved per ton of material. And so it's not about the technicalities, it is about the way we operate these sites. And a similar example, you can look at timber, right? Timber theoretically can be reused very well, and I'll show some examples, but the way we break down our materials in the process, we're reducing the material value to 0 because we're breaking those pieces into small particles. And so that brings me to the first project that I wanted to show you. In the lab, we just simply said, okay, what would be an alternative? An alternative to demolition is deconstruction. Deconstruction is not an alternative to building reuse or adaptive reuse or building preservation. I just want to make that really clear. We're not promoting the disappearing of buildings. We're simply saying if a building reaches the end of life and there's no alternative than clearing the site, then deconstruction is your sustainable alternative to demolition. And so one of the questions that we wanted to answer is how can we overcome the stigma that deconstruction is more expensive and more labor intensive than demolition and thus cannot happen at scale. And so this is a project in Ithaca where we convinced the developer of a large 300-bedroom housing unit to deconstruct one of the houses that he needed to clear in this site. So you can see he demolished 10 buildings while we got one to deconstruct as a case study. But the deal was we need to be as quick as his demo crew, because if they catch up on us, they will just demolish it. And so that set quite a big pressure on us, and we shifted from like the stick-by-stick unbuilding process of the building to mechanized, panelized deconstruction, which essentially cuts the building into the largest possible elements that you can still put on a flatbed truck to then ship them off-site and disassemble them in a warehouse, right? Similar, the reverse of like modular construction or panelized construction. And so it took us 4 days to take down a 3-story, 13-bedroom house, which essentially at the end of the 4th day looked like this, the whole house staged outside of the local reuse center. And then we went at it and analyzed the data and worked on publications, and worked through the material and started reselling that material. And in the end, it turned out that the difference in cost that we had in the operation of the site was we were able to offset that with the revenue that came from the resale of the materials. And so now you're cost competitive and you're time competitive, right? And that's the good news, because now we can talk about the things we really want to talk about with deconstruction. It's the social values, it's the reduced air pollution, it's the workforce development that happens, it's the local job generation that happens. So these are images from the deconstruction site where we trained local carpenters in the strategies of deconstruction. We, in this project, only employed union labor, so this is the local union apprenticeship program that was training on this deconstruction project. And then we started doing deconstruction workshops for students on different projects, learning from these experiences. And this is, of course, a fun experience, but there's also sort of a pedagogic value in this, because if you've struggled for a couple hours to try and get a piece out of a building, and that piece wasn't meant to be taken out, right? It was glued in there, like lots of spray foam, and I don't know what you want to do, right? And then you go back to the drawing table, you draw a different detail, right? You don't draw spray foam, right? Because you've just struggled with it. There's a couple other things that this building taught us, and those have to do with what are the limits to scaling deconstruction. And so one aspect is that we tend to not know what we're going to find in a building. Documentation is missing. If we have any documentation, it's a nice hand drawing in the archives of the city, where you essentially have a thick black line that represents this is the wall section, right? But you would never know what are the layers, what are the actual materials in this building. And so we started to think about what can we do with technical means to make this process a bit easier, and developed an app which we call Scanner, which essentially combines a tool that now most of our contractors have in their pockets. Tablets or iPhones all are LiDAR scanners by now, and so can we use these really low resolution LiDAR scanners that are available to almost anyone now, in combination with a database of construction archetypes, to very quickly estimate what is the content of a building, what are the tonnages that we're expecting to come out of a building, what is the embodied carbon values that are associated with these materials. And we're not saying that this is bulletproof and this data is all correct. What we're saying is it gives a contractor really quickly more information for an informed conversation about deconstruction or demolition. Right? So it's just a way into a conversation that we want to have and that we tend to not have because of the limited data availability. And so you can have a conversation with your building owner or your architect or your deconstructor or your permitting officer about the benefits of deconstruction. Now, the interesting thing is, once you can do that on a building level, you might think about the city level, the urban level. And so we started a project together with the Environmental Systems Lab at Cornell University to build a digital twin of Ithaca. Ithaca is an interesting case study because it has one of the most progressive environmental laws in the nation. The agenda is to decarbonize all 6,000 structures in Ithaca by 2030. That is also tomorrow, and I'm not sure if we're going to get there. But it is an incredibly ambitious goal that drives a lot of research and movement. And so we're helping the city, and the city is helping us to kind of figure out what are the right questions to ask, what are scenarios that are important to model. And so we're using similar techniques to understand what is the material content of a city, what is the makeup of these structures, what are possibilities in terms of the use or the continued reuse of these buildings, and what are scenarios when you start upgrading in terms of the materials that you take out and the materials you have to put back in, right, in the renovation process, and how could we close the loop on those. And then the last question that we can answer at this level is, it's not just about how much timber is in a building or how much concrete is in a city, but which part of that is accessible, which part actually has value, and so we can start calculating circularity indicators for buildings, for material groups, or for components on the city scale. Now, as I mentioned earlier, none of this is possible to do alone, and we're shifting more and more, or all of this sort of made obvious that we need policy and code to follow suit, or to support us, or to create a framework that we can operate in. And so we founded in 2020 kind of an advocacy group that we called CROWD. CROWD is an acronym that stands for Circularity, Reuse, and Zero Waste Development. It's a group that came together out of the concerns about demolition in Ithaca, but then very quickly grew to a statewide organization that now has several cities and municipalities in it, but also for example, the New York State Preservation Association, a lot of research labs, reuse centers, industry, NGOs. And so we started meeting during COVID every Monday morning at 9, and we're still now meeting every Monday morning at 9. And that is an incredible tool to move agendas or understand where we should act, because all of these different agencies have their feelers in the conversation and can report back. And so as a group, we, a couple of years ago, realized we need to put out a white paper that kind of estimates the potential of this on a state level to convince people that we need to change policy and legislation. And so we just published a white paper. It's titled Constructing a Circular Economy in New York State. It's freely available. And the goal really was to, first of all, understand the status quo. Where are we? What is the data? How much waste are we generating, et cetera, et cetera. And then going from there, do economic analysis of what is the potential, and our estimates are that if we were to shift about 70% of residential demolitions to deconstruction statewide, there's a $3 billion economic impact of that, and about 13,000 jobs that could be created. And so suddenly we're realizing, hey, that there's something there that actually might make people aware of a possible shift. And then we followed up with 19 policy recommendations on how this shift would be possible. And these policy recommendations essentially follow all the life cycle moments of a building. So how do we build a workforce that does that? How can we build a market for those materials, right? Because if you just take a lot of materials out of a building and they don't have anywhere to go, then that doesn't scale either. How do we build the infrastructure, right, to do all of that? How can the state lead by example? It's interesting, in New York State, for example, the university system owns about 40% of real estate statewide. So if they change, right, there's an enormous budget, an enormous capacity of buildings to lead by example. And then questions of how can we sustain that circularity moving forward. Part of this is also the recommendation for a deconstruction ordinance. We developed a template deconstruction ordinance that now has been used already in 2 municipalities, Auburn and Dryden, throughout the last year, to be passed by the city and town councils unanimously in both cases, to shift really from deconstruction to from demolition to deconstruction. Now I mentioned I'm going to talk about the 3 parts, right? So now we've created a lot of material. The question is, what do we do with that, right? And so I wanted to show a couple projects. This is a project from our office in Germany. It's called the Mehrwert Pavillon. It's a pavilion that we built for the Ministry of Environment in Baden-Württemberg. for the Federal Garden Show, which is a massive event that happens every 4 years in Germany. And they asked us to build a pavilion only out of secondary resources. So all of the materials in this pavilion are either recycled or reused. There's no virgin materials. And so we decided to kind of split it by material families. The shell is made out of recycled glass. The structure is made out of directly reused steel. Then we have all the furniture is recycling plastics, in this case recycled household plastic waste. And then we have all the ground and the foundations out of reused or recycled mineral waste. And just to give you a couple visuals of how that looks like, none of this is really reinventing the wheel. We've removed plaster stones from one location to the other for centuries, right? But the question is, how can we implement that as a strategy across different projects? What you see here is the white is ground down ceramic waste that would have otherwise gone to landfill from the production of plates and cups. And we found a way to grind it and sieve it at a ratio similar to concrete construction that turned into a water-bound surface, so there's no adhesives or glue in it, and it sustained 1.2 million visitors over the period of that exhibition. The facade, as I mentioned, is recycled glass. Much of this is sintered glass, which means that it's using resources like bottle glass or car window shields, but it sinters them at a much lower temperature than you would usually do with production of new window glass, right? So we're at 800 degrees Celsius. The new window glass usually needs 2,300 degrees Celsius, so the energy impact is much lower. But what we believe is also the aesthetic value is there because it creates a glass that you couldn't produce otherwise. There's no way to make this glass from virgin resources because you need the shard to start with, right? And so it translates a history and it creates something unique because of the process that we used here. The most interesting about this project is the question of the steel reuse. Recycled steel is the norm. The question was, can we push this a little bit further? Can we make sure that there's no new energy input in the reuse of that steel? And so we had an interesting source because all the steel that came out of this project comes from a former coal-fired power plant. Germany's shutting down its coal-fired power plants because of the shift to renewable energy sources. And now we have these structures standing in the landscape and no one knows what to do with it. It's massive infrastructure that is now obsolete. Unfortunately, the standard answer is we're going to demolish this, and they did. But before they did, we were able to pull out enough steel to build a small pavilion. The problem was we had no idea what kind of steel that is, right? There was no documentation, and so without documentation, no building permit, right? And so we ended up having to do 5 tests, most of it like chemical composition, weldability, tensile tests, compression tests, kind of specify the material qualities of the steel to in the end find out this is standard structural construction steel. And the moment we had that answer and we had it signed and on paper, we got a building permit to build with it, right? So that the point here being there is nothing in the code that specifies virgin or primary. There's no difference from a code perspective. The only thing you have to fulfill is you need to create enough information to specify that you're fulfilling the criteria that the code specifies, right? And so in this case, we then were able to build this structure out of these tubes that held this pavilion. A kind of side note is that, of course, this pavilion would have never looked the way it does without a very specific material stock to work from, right? And so the design process with reclaimed materials is a very different one from a normal traditional design process where we first come up with a form and then we open the catalog and we pick the materials that will fulfill that form, right? In this case, it's the flip side. You first have a material and you need to figure out how do you design with that, what kind of forms could you build with it. And it's a really interesting exercise and one that I hope will become the norm moving forward. Similar project, but in a very different context. This is a small pavilion that we did at Cornell University. Here we reused part of the materials that we salvaged from the deconstruction project I just showed you a couple minutes ago. And this is a little pavilion for an arts biennial at Cornell University. It looks very small, but it is large enough to require a full building permit by the city of Ithaca. And that actually turned out, in the end, as much work as it was, it turned out as something really positive, because it required us to think through the process of what does it take to get a building permit for structural reuse of salvaged timber, which is by code not allowed in New York State. And so working through that essentially opened up 3 new research projects that we're still working on moving forward. It, of course, started with the process of how do we use these materials, how do we process these materials. We took out all the nails, there's lots of hand labor in this, questions of the aesthetic of cutting through it, the old patina, the new cut. There's a lot of sort of aesthetic questions that we thought about in how to use this material. Then again, there's sort of a data-driven answer, a question that arose from it, kind of where did the material come from, and where is it now, and where is it going next, and how do we create a material passport for these materials, and how do we connect the digital and the physical, which is a really difficult question, as it turns out, to continuously link a digital twin to its physical representation when you start messing with the physical, right? And the items go different places. Or how do you design with a stock that is not uniform? Material tolerances, for example, were up to about 1/2 inch. And so if you design a detail that depends on the fact that you need this tolerance to be near 0, none of this fits together in the end. And so how do we change our detailing that it adjusts to this new type of stock that we're creating through deconstruction? At the end of the life of the structure, we had to take it down. Of course, it was on university grounds. The space was needed for something else. But we were invited to rebuild it as part of the permanent collection of Art OMA, which is a sculpture and architecture park near Albany. And of course, the site was different, and so our answer needed to be different. And so we were able to reconfigure the structure because it was designed for disassembly. All the details were possible to be readjusted. And so this is how it now looks currently in this sculpture park. I mentioned that there's research that came out of this. So the first question that we tried to answer, what are the correct engineering design values when you work with structural wood? It turns out that the standard process would be you go into your book of specifications, you look up the design values based on your species, and then you use those design values to calculate the dimensions that are required for the specific load. Right? The problem is we don't know what the species is, right? And we send out samples to 3 national experts, and we got 3 different results. Right? And so that sort of said, okay, this doesn't scale. How can we move forward with that, right? And so here's 3 different other paths of how this could work. We could go, of course, we can do structural testing, right? But then we lose a certain amount because that's destructive testing in most cases. We can go by the specific gravity, or basically the density of the material. We can do a sort of a midway with some testing and some assessment. But it turns out actually all of it revolves around the density. So the quality of the material actually makes the biggest impact, right? So and so that's good news. The density is something that everyone can easily test, right? All you need is scale and a tape measure. So that's interesting. But out of that conversation, again, came the question: how can we implement something at a larger scale, maybe? And we learned that there's two states that have legislation that allows timber reuse. Not surprisingly, that's Washington and Oregon, because they have a phenomenal old growth timber in their built environment. And if you deconstruct a house in Portland, Oregon, you get a value out of it that's probably much higher than anything you could buy right now in Lowe's or Home Depot, right? And so they always understood the value of these timber elements, and now basically allow the direct reuse of these elements through code, because it auto-assigns it auto-assigns a grade 2 to any timber that comes out of a deconstruction project. Which is a structural grade, and you can do stick frame construction with that, right? And so you can start building residential houses without having to reapply or regrade the timber. This bill is doing something similar. It's learning from the precedent in these two states, and is in both the Senate and the House right now for discussion in New York State. But there's something maybe that machines can do for us in terms of visual grading. And so another project that one of my PhD students is working on right now is the question, can we use AI to do visual grading of lumber? Because in the end, it's a very, very technical and very prescribed process, right? You're counting knots, you're counting the size of the knots, you're counting the distance of the knots, you're counting the length of a crack or a check or a split. And if we find a way for the machine to understand and detect these defects, we could use the machine to do the grading for us, and it actually works phenomenally well. So we have a process now in place that does the visual grading and detects these things. And the next step is to now integrate this into the inline process of Urban Machine. Urban Machine is one of our industry partners that developed a robot to denail lumber. So the robot pulls out the nails. And what we're hoping for is that essentially now at the end of this process, you don't just have denailed lumber, but you have denailed graded lumber, right? Because at the end, as the last step, the machine puts the stamp on it because we know what quality it is, right? And the interesting thing, going back to the conversation about steel, right? That bypasses any new requirements for building codes, because the moment it has a grade, it goes directly into the market and can be used like any other timber. And the last step in this is, what can we do with all the smaller pieces, right? Because what I just showed you assumes that we're pulling out nice joists, 2x10s, and beautiful material. That's not always the case, right? Sometimes you end up with a small piece and you don't really know what to do with it. And the answer to that, of course, is engineered timber products. That's essentially what the industry does already. The problem with those is, from a circular construction perspective, is the adhesive, right? It's full of adhesive, potentially VOCs, undetermined end-of-life strategies. And so what we're trying right now is something we call groove lam, which is essentially using a mechanical interface between the layers and fasteners. In this example, it's plastic straps. They turned out not to be the best solution, but they're the most visual on what it does. It just holds together these two pieces, right? But we're creating some really interesting large-scale beams that are engineering products, engineered timber products from shorter length and shorter dimensions, but that can span large dimensions. And we just won a grant, NYSERDA grant, with a really phenomenal collection of industry partners to scale this process, and we're working on the design for 2 case study projects, one in Brooklyn and one in upstate New York, to really reuse deconstructed lumber for larger spans in actual two case study projects. And then there's the third question, right? If we're not just using salvaged materials, that's one part, but the question is, how do we design differently so that buildings in the future can be disassembled easier, right? So that we don't have to deal with all the problems that I just explained. And so there's one case study that we built with the office again in Switzerland in a collaboration with the office of Werner Sobeck. And it's called the Urban Mining and Recycling Unit. It's essentially this piece. The larger structure is called the Nest. It's a really interesting research infrastructure that EPFL, that's the former material testing agency of the Swiss government. It's now part of ETH Zurich and became sort of a material research testing laboratory. And they built this structure that allows for one-to-one, full-scale modules to be pushed in to test different ideas. And so they came to us and said, well, you published this book, Building from Waste, and does that actually work? And could you prove it? And can you build a building that is designed for disassembly? And so the brief was very clear. Any material that goes into this house has to be able to come out and go back into their original material cycles. No waste. It's a very academic brief for a full-scale actual construction. And so we tried to push it as hard as possible, and we had the phenomenal position that our client supported this research and had the money to fund some of these more extreme solutions. But so essentially the first step was, okay, we're going modular, right? Makes sense because if you have modular construction, you have the control of the warehouse. You don't have someone cutting a piece of timber on a side and that already goes into the trash. Right? And so if you want to reach 100%, you need to have that full control. And so in the end, we built 7 modules that were then lifted into the site within 1 day. That's the other benefit. We had a 1-day construction site. The client was extremely happy. They didn't have to shut down operations. They just basically closed the building for a day and then reopened with another module attached to the interior. But the benefit of the assembly plan of the module is that it is also the disassembly plan. Right? So you already know which materials are where, how are they connected, and so that involved this kind of design for disassembly idea. And then we were wondering to answer certain questions. For example, can we build brick walls without mortar, right? And so there's an answer to this. This uses bricks that are made out of construction waste. It's a company called Stone Cycling from the Netherlands that is selling bricks that are called wasabi or aubergine or salami based on which particles of demolition waste they're putting in. So the bricks are sort of the salami pieces, and it's a beautiful product. But we worked with them to develop a unique brick that has a tongue and groove system and holes for post-tensioning bars. And so there's a structural wall that is made entirely from a mortar-free brick construction. What I mentioned earlier, the really tricky part was, can we do wet areas, bathrooms, kitchens, without silicone, without mortar? And so all of the connections in these rooms are dry gasket sealant. It's just pressure with 2 screws at the top, and the largest possible formats to reduce the amount of connections that we had. And so this brought us back to glass ceramic, the material from the pavilion, but then also an alternative. These are former kitchen cutting boards that are turned into this beautiful sort of fake high density polyethylene marble interior wall. But it went further. The question was then, okay, what are the faucets? What are what's the equipment? And we did not find a single faucet on the Swiss market that fulfilled the requirements of design for disassembly. Faucets are usually elements that are press-fit together out of at least 3 different materials. Like you have a copper pipe in the middle, some kind of casing around it, you have plastic pieces for the movable elements. None of this can ever be separated again, and so the faucet ends up on the landfill because you can't do anything with it. And so we worked together with Arva, which is a part of Laufen, one of the larger Swiss companies for bathroom equipment, to 3D print out of stainless steel. So these are monomaterial faucets where all the moving parts, everything is printed in one go out of one material. And so, of course, the idea here again is we can use this as long as possible. We can polish this. This is a high-quality product. At least it should last for years. But if it ever ends this life, right, we can reprint something else out of it because it's exactly the same feedstock for the same printer as it was in its first production. There's just a couple of ideas. There's 24 materials in the unit. They're all really well documented. It has its own website. We have also a physical material library in the unit that shows a little bit more examples with data sheets, and then we started doing a digital representation of that. This is called a material passport or a building passport. This was pretty early in the conversation of material passporting. By now, this is actually a requirement for any new construction in several European countries. When we started this, it was an idea. And the interesting thing for us, and the reason why I'm showing it, is because it came way too late in the process, right? So we first built the design, and then we said, oh, let's make a digital representation of it and store the data so that at some point in the future, someone can access that data and decide how to best reuse the product. But what we noticed is that the circularity analysis that is embedded in this design, in this data set, could have helped us make better design decisions if we had this data much earlier in the process. And there's no tool that allows that. At least at that time, there was no tool, and so we started doing our own. This is Rhino Circular. Rhino Circular is maybe most helpful to the students. It's free for download on Food for Rhino. It's essentially a Rhino plugin that calculates the circularity of any design that you're feeding into it. And you can do that at a very early stage. You can essentially use it for a massing model where you just have a block and you assign 3-4 materials to the different sides, and you get a starting point of a conversation. But you can get to a very detailed analysis, and it can feed back circularity indicators in graphic representation to those details. So you can say, well, any of the materials that are problematic, they should light up in red or in green in your geometry. And so you have a very immediate feedback while you're modeling on circularity questions in your design. And then, as a last project, because the lecture is called Deconstruction and Cultivation, I wanted to show you a project that is made out of mushroom mycelium. That's sort of the third part. How can we regenerate nature? How can we use, in those cases where we don't have salvaged materials, right? How can we use other types of materials out of nature as a resource? And the thought process behind that is we're never going to have enough materials from deconstruction to sustain the hunger of new construction. There's always more new construction than there is deconstruction, right? And so what do we do with that gap? And that gap is timber, but it cannot only be timber because that's not sustainable either, right? To focus on a monomaterial actually got us where we are. The fact that the industry at some point shifted to construction as the one and only, to concrete or reinforced concrete as the one and only material globally of how we build is one of the reasons why we have the problems we have right now. And so the more heterogeneous we are, the better. And so when we talk about the sort of possibilities of biomaterials, mushroom mycelium is one possible option. The way it is used is essentially the organism is a dense network of hyphae, which we're using as a biological glue to hold together substrate. And we're not the only ones. There's a lot of mycelium research going on in the world because it's a fascinating material, and I think we've only touched a small percentage of what mushroom mycelium can do for us, or what mushrooms in general can do for us. I mean, several of you probably saw fantastic documentaries about the world of fungi. And so there are millions of different species out there, and they all have different qualities, and we don't yet know entirely what the potentials are. But we've been at this for quite a few years now. 9 years ago, we opened this pavilion at the Seoul Biennale, which is called Myco-Tree, and essentially at that point in time said, well, mushroom mycelium is really good in compression, but it's really bad in bending. And so how can we find a form that is loaded in compression only? And we worked with Philip Block and the Block Research Group to determine this structure, which is optimized for its load behavior so that there's no bending at any moment in this tree. It's a pure compression curve, essentially the inverse of a volt. And then we had this roof that sort of held it all together. But since then, we've sort of continuously evolved this material. And so the next project that I'm showing you is again part of our Cornell research. And the question was, is there a way to make panels, load-bearing panels that do take some bending, and how can we build with those? And so we've done research for the last couple of years on this question, and I think we've gotten to some point in time where we can show these results. And we showed them as part, again, of a pavilion, as a kind of demonstrator. And we were invited to Buildfest, which is a fantastic event in Bethel Woods. Bethel Woods is the original site of the Woodstock Festival. Woodstock was planned to be in Woodstock, and then in the last moment had to be diverted to Bethel. That's where the name comes from, but it never happened in Woodstock, it happened in Bethel Woods. And this is an original picture from 1969 of the site that we were allowed to build in 2025. And so this is how this looks today. The swing is gone, the tree is still there, part of it is on the ground. So the question was, how can we build on this side something that is part of a pavilion structure, of a festival structure? Interestingly, the reason why this Buildfest has been restarted is that at the original Woodstock Festival, the structures that we all know, or some of us know from pictures, were built by students from the University of Florida. So already at that point in time, the idea was, let's bring students together to build demonstrators to sustain this festival with their structures. And so the revamp of Buildfest since the last 3 years is essentially doing the same thing. They're bringing together student groups from 6 or 7 different universities to build designs in a week at this site, while camping there, and there's a band playing every night. So it's a phenomenal event. If you have the chance next year, submit a proposal. It's really worth it. So to get to the point here, we decided that we want to build a mycelium structure in this site that essentially sort of comes out of the forest using local resources, and then at the end of the festival goes back to the forest by biodegrading into the site, right? Because it doesn't use any foreign materials, it's all local, and so that's really sort of the biocycle as a building. And so again, we use sort of the Wold as an idea to structure this. This is the site, and it's kind of split 3 arches. And then we started building this using our own fabrication labs. And for those of you that are not familiar with mushroom mycelium, it's a pretty long process because you're actually growing a material. And so you need weeks and weeks to do that. And it can be pretty frustrating because at some point the growth maybe of some of these doesn't work, or you have contamination. And so there is much to still learn on how to grow materials at this scale. But the timeline essentially uses the inoculation in the petri dish then the mixing of that substrate with that inoculation, you grow it in frames. You can bioweld mushroom mycelium, and I'll get to that. And then you basically get these long arches, and we can then set them up on site during the festival. And to just lead you through some of this, so this is the moment where the inoculated mycelium gets into the bag with the substrate. The substrate in this case is local hemp and straw from agricultural production right next to Cornell. So all of this is like a 5-mile radius. We actually picked the strain from a tree in front of the biology department on the street, so it couldn't get more local than this. And then we're growing this under controlled conditions by something like 27 Celsius and 70% humidity, sort of perfect growth conditions for mushrooms. And then to reduce the environmental impact of this, at some point you need to dehydrate that, but we didn't want to use ovens. And so we built solar ovens to dehydrate the material. And then at some point we had to press it, which is then a sort of low-tech constructed hydraulic press that we used for that, to then create these microplies, as we call them, which are reinforced with a layer of burlap, and that burlap is then also used for the connection details. And in the end, it looked like this. This was the fresh and new pavilion right at the opening. As you can see, it really turned into a kind of community event, similar to like a barn raising to get this thing to stand. But I'm going back every couple weeks and months to kind of document the process and see, does it start degrading, or do we go back into the forest already? And this is a picture from the middle of the winter, and it actually looks still really good, surprisingly good, and we're really interesting to follow that narrative for the next couple months and years, hopefully to see what happens to that material. I'll end it here and look forward to your questions. These just some shameless plugs. If you want to know more, they exist, and I'm happy to take your questions.
Right, can you hear me? Good. All right, I get the pleasure of taking questions from the audience, so I'm sure there are wonderful opportunities for y'all to share your thoughts or ideas, and put your hands up and I'll bring you the microphone. Way in the back, because I know you can't hear from way in the back.
Can I just see that slide with the shameless plugs again? Thank you.
I spoke to your librarian today. 2 of those are in the library, and the other 2 will be in the library very soon. So you have resources.
With the mycelium growth blocks, have you found that it needs to maintain a smaller form in order to be stable, or have you been looking for larger form research type?
That's a really good question. I don't know if you had experience with mushrooms mycelium before. It is a natural growth process, and so it needs oxygen, or in this case actually partially also CO2 to run this process. And so the problem that we're facing is if you get too large, the center doesn't grow because the oxygenation doesn't work, and you don't get the oxygen deep enough into the material. And so part of the goal of this research is to reduce the size of the individual layer, right? Make thin layers, and then layer these to a larger composite material. And I mentioned I'll explain biowelding, and then I didn't, so that gives me the chance now. So what the interesting thing about mushroom mycelium is that it's still alive while you're doing all this, right? And so if you layer these living layers of, or plies is probably the better word, you layer these plies of living material, they start growing into each other. And so that's the term that we're using, is biowelding, right? But it is just a normal growth process. And so in the end, you actually get a homogeneous material that has a much higher strength than if you were to basically fill a form to the same dimensions in one ply. There's really interesting research out there to say how far can I push this. The largest ever monolithic mushroom structure is 10 by 10 by 10 feet. It's a solid cube by one of our colleagues, and that didn't work.
Thank you.
With how detailed and like specific you have to be for circular, construction, are you seeing like a lot of companies trying to develop this, or do you think a lot of them are gonna kind of ignore it and like keep doing what they're doing for the sake of, I guess, what they think is efficiency?
Yeah, good question. It really depends on the framework that these companies are operating within. There's some fascinating new companies, mostly actually startups, coming out of Northern Europe, where you have sort of a legislative framework that requires these materials. And so they have a market, right? And with it have a business model to sustain their company. One of the examples that I showed, stone cycling, is from Amsterdam. And the Dutch government put out a requirement for the whole nation to be carbon neutral by 2050, which is still far in the future, but all of the legislation is sort of moving towards that goal, to a point that Amsterdam, for example, wants to be carbon neutral by 2035, which is actually closer than almost tomorrow, right? And so the choice of materials in construction becomes really important. How can you build carbon neutral? How can you build carbon negative? And the material selection helps in these conversations. And so these companies have a market. Several of them are trying to come over here. We've spoken with some of these companies to kind of create manufacturing plants or start building a market in the US. So that definitely happens. And I think it will happen more and more, despite of what is happening at in the world right now. Because the demand, I think, is still there, right? I think more and more clients and architects are demanding for materials that fulfill sustainability requirements. And so maybe the reasons are different, right? Right now, maybe it's more personal agenda than requirement, but I think the market is growing, and with it, the potential creation of new business models for those. The largest, there's a couple of really large demonstrator projects in the US that are extremely successful, and I think that point to the viability of this. Boulder, Colorado, for example, deconstructed a hospital 2 years ago, which is probably one of the largest structures we can deal with as architects, right? And then reused all the steel that they salvaged from this project to build the local new fire station and a local new school, right? Also pretty big projects. So it's definitely something that is much larger than what we can do in the lab as a demonstrator. And then the other project that is worth pointing to is the Sparks project in New York. The New York City Environmental Development Corporation, NYCEDC, put out circular construction guidelines last year that require that if you want funding from the EDC, right, and that's their tool, then you need to fulfill these guidelines, and they actually specify a waste diversion rate of 75%, They require a reuse percentage of, I think, 20%. And those are not easy goals in the New York context, especially in the New York City context, which has a very different makeup of the built environment than what we're dealing with in Ithaca. And that project is at the moment at a really crucial, so the Sparks project is the first one that applied for this funding, and so now this demonstrator project within these new set of guidelines. And that's like a 100 million square foot project that is being deconstructed and then built into housing. And they're at a crucial moment right now where they're basically asking for RFPs from companies to take out these materials. And that will either work or it won't, but if it works, it will scale, right? Because it develops a pathway. And so we're all really engaged in trying to make this project a success, because it is sort of a pathway towards industry implementation of these ideas.
So I was really interested in how you explained how the carpenters, you kind of retrained them how to shift from like the demolition to the deconstruction. So I would just kind of love to know more about like what that training like entails, and obviously like different buildings are going to be different, so like how you kind of differ the deconstruction approach depending on the different building.
Yeah, also a good question. The goal, first of all, the goal of demolition and deconstruction are fundamentally different, right? So a demolition's goal is to clear the site as quickly as possible, versus a deconstruction goal is to clear the site while retaining a maximum of economic and utility value of the materials on the site, right? And so the training is very different, and it's almost it's much closer to a carpentry training than a machine operator training, which is more on the demolition side. There are several different deconstruction certification processes in the US. Just 4 months ago, a union apprenticeship program for deconstruction has been approved at the federal level. So this is something that companies can now tap into and say, well, there is the whole setup of how to run these workshops, right? And how to accredit these workshops. And so that infrastructure hopefully will become a driver for the scaling of that workforce. The most successful deconstruction trainings that I know of are run by a phenomenal business out of Savannah, Georgia. They're called Repurpose Savannah. It's a only women-run company that does deconstruction projects, and they are traveling the nation and building sort of a workforce through trainings. Phenomenal people. And then the question, why would you do a deconstruction training, right, has to do with policy. So the first deconstruction ordinance that was approved in the country came from Portland. That was approved in 2016. And then they started training deconstructors to do this job, and now have 17 certified deconstruction companies listed, and they are the ones that can bid on these RFPs. And they have clear data of how the growth of this industry impacted the amount of structures that are being taken down, the amount of material that is being reused, but also sort of how many projects you need to sustain an industry of 17 businesses that need to make money, right? And so it has to do also with how many projects do you actually have in a town per year to see how many deconstructors can that business sustain, right? The second example is maybe San Antonio, which is the 7th largest city we have in the nation, and they implemented a deconstruction ordinance in 2022. there it requires only residential buildings that were built pre-1940s to be deconstructed, but that's actually quite a few deconstruction projects. And so they're starting to grow in industry, and actually Repurpose Savannah is the one that trains the contractors in San Antonio now. And so the reuse world is small, and you get to know many of the actors very quickly, but the relationship between deconstruction training and policy and sort of the scale that it can reach is very direct. Right? The worst thing that can happen is that you require deconstruction without having the capacity to do deconstruction, right? Then the whole system flips because it creates frustration, it creates an enormous price tag for the deconstruction. If only one company can do it, right, for example, they can charge whatever they want. And so building the capacity in accordance with sort of the policy development is a crucial part of this shift.
I'm curious what your next mountain to climb is.
The next mountain is, I've just today been in conversation with a New York State Assembly member on the drafting of another bill that we want to submit hopefully soon, or that they want to submit hopefully soon. That is essentially bringing together many of these 19 recommendations that we outlined in our white paper to really change how New York State is operating. That's a long shot, it's a big mountain, but I think there is a tremendous potential in legislation like that.
Is there a material conundrum that's frustrated you, that maybe a related mountain?
I think I don't know if it's still a mountain. What we're really excited about is the automated regrading of lumber, because it's a technical solution to what seemed like an enormous problem, right? We have all this lumber that we potentially take out, and we always thought we need to change the policy and we need to change the code to actually allow for all of this to find a market. And if we can actually just regrade that lumber and bring it into the market as is without having to change all of this, right? It's so much quicker and so much easier. And so that the potential of that technology is enormous from the way we look at it.
All right. Well, wonderful, wonderful presentation. Thank you again.
Thank you. Thanks for the invitation.